Hello, class. What we're going to do now is we're going to take the molecule ethane and we're going to look at its Newman projection. Okay? This Newman projection would look like this. Where we have all hydrogens. So that's our Newman. And so what we're going to do is I'm going to take, well, first off, let's see here. So what we're going to do first is when we look at this Newman projection, if I look at these two hydrogens right here, this one on the front carbon and this one on the back carbon right there, what we have is an angle between those two groups right there. There's an angle. That angle right there is 60 degrees. And that angle is called a dihedral angle. Let's make sure we spell this right here. So we have a dihedral. And it's this dihedral angle that we are going to track in this little graph here on the x-axis. We're tracking the dihedral angles. This dihedral angle is also called the torsional angle. Let's see, I think I misspelled that one. I did. Let's see here. Yeah, okay. So we have dihedral angle and torsional angle. They're one and the same. And that is looking at groups between, you can ask what is the dihedral angle between any groups, okay? You could have very well have looked at the angle between this guy and that guy. As long as you're looking at a group in the front carbon, attached to the front carbon, and one in the back carbon. So what would the dihedral angle be between those two? That would be 180 degrees. Right? So when we are looking at our ethane molecule, what we're going to do, so I can show you the different energies here amongst all these groups here. Let's see, maybe it's just easier to erase it all real quick. Okay, like that. So what we are going to do is I'm going to color code these hydrogens here. And we're going to track these two. No. I want to color code it. I'll put them in pink. Okay. So what we're going to do is we're going to, I'm just double checking. Okay, so what we're going to do is we're going to keep the back carbon, the circle, constant. It's not going to rotate. The back carbon is just going to stay there. What we're going to do is take the front carbon and rotate the front carbon. And so we're going to be moving this pink hydrogen to different spots. Okay? So what we have here is the Newman right here. You can see the dihedral angle between this pink hydrogen in the front and the pink hydrogen in the back is 180 degrees. So that goes right here. And so just to save time, I'm not going to draw in all the hydrogens. I'm just going to draw in the ones of significance. That's a dihedral angle. So these right here, these four, those are hydrogens. I'm just not going to draw them in just for ease, okay? So we have a dihedral angle of 180 degrees. However, this conformation right here is really, really important because every single dihedral angle, every single one in this conformation is 60 degrees. All right? So I know that may be sounding confusing, but let me restate it and see if we can make sense of it. What is the dihedral angle between the two pink hydrogens? That is 180 degrees. Okay? But now for a moment, just ignore that these are pink hydrogens. Just think of them all as green hydrogens. When all the groups have a dihedral angle between their adjacent groups, when that angle right there is 60 degrees, we call that a staggered conformation. So this guy right here is considered staggered. All right. So that guy right there is a staggered conformation because all the dihedral angles are at 60 degrees. Now, let's take the front carbon and just move it, the front carbon, and rotate it clockwise 60 degrees to my right. What's going to happen here? Well, I can definitely say that the back carbons are going to remain constant. So that would mean that the pink hydrogen right there just stays, all right? And then if I take the front carbon and rotate it 60 degrees to the right, what do I have here? Now this is the tricky part here because we're going to have it like this and like that. Maybe I should have drawn the front carbon first. Let's try that. Make that look a little bit better here. Okay, so we have this, this, and that. And the pink hydrogen is there. And then in the back, those are all constant. Those did not move. Okay? Now when we look at this conformation right now, what is the angle between the two pink hydrogens? Okay? That is 120 degrees. That's what this number right here is showing. That angle, the dihedral angle between the two pink hydrogens, 120. But when you look at the dihedral angles of them all, so if you look at the dihedral angle between that group, just in between there, and in between there, that's really not an angle because this hydrogen, pink hydrogen, is directly behind this hydrogen in the front. So this has a all the groups in this molecule have a dihedral angle of 0. And when you have dihedral angles for every single group on that molecule, we call that a eclipsed. We will use blue here. So this is a eclipsed. EC. So this is a eclipse conformation. This is a staggered conformation. And the conformations that are the most important to us in ethane are the staggered and the eclipse, because those are the two extremes between the conformations here. We have it low energy, high energy. So what have we learned? Staggered conformations are lower in energy. Eclipsed are the highest in energy. So we can continue just doing this process all the way through this analysis here. So I'm going to pause the video and just draw out all the conformations. And what you're going to do is just track that pink hydrogen in the front and watch where it goes. Okay? Okay, so now just look at where the pink hydrogen is going. So we talked about this one and this one already. So starting from this eclipse conformation, I've just taken the front carbon and rotated 60 degrees. And now look at the dihedral angle between the two pink hydrogens. It's 60 degrees. But then when you look at all the substituents or all the hydrogens on the Newman projection, they're all at 60 degrees. So that makes this guy a staggered conformation. Eclipsed. You can see that the dihedral angle between the two pink hydrogens is 0, but all the dihedral angles are 0, so that is eclipsed. Staggered, eclipsed, staggered. Now the energy difference here between the staggered and the eclipsed, so I'm just going to draw a dotted line here, and look at that energy gap right there. That energy difference is 12 kilojoules per mole. And so that's not a major energy difference. And so there's enough energy at room temperature for the molecules to be rotating constantly. They're constantly spinning, just going through this whole process. Just fast, 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 fast. And so these molecules here, they're not stationary, they're not stagnant, but they're spinning. Constantly spinning. And so we have okay, so you know the energy difference, that's important to know. Now what we need to figure out is why is there an energy difference? Why is the staggered more stable, lower in energy than the eclipsed? And there's some debate on what that's all about. But let's look at it this way. So I'm going to draw a larger Newman here. We'll do it in this corner. We'll see if we can get this to work here. So why is let's look at it. Let's see here. Okay. So we have a hydrogen here, right? And then we have a hydrogen there. We'll draw it in the staggered conformation here. Why is this lower in energy? Well, let's just think about it for a moment here. In the fact that this carbon, this hydrogen, there's 2 electrons between those 2 atoms, right? And electrons aren't a line, they're an orbital. And so you could represent it more like an electron cloud. Okay? And so we have the electron cloud right there on that front carbon hydrogen. But then we also have the electron cloud of this guy right here. Okay? Between that carbon. And in the staggered conformation, we can get these 2 electron clouds the farthest apart as possible. Because those are electrons right there, right? They're negatively charged here. And so if you get 2 electron clouds really, really close together, there's going to be repulsion, and there's going to be an increase in energy. So you could envision now, if I redraw this, and draw it in the eclipsed conformation, Okay, there's the eclipsed. And if I'm representing that hydrogen and that hydrogen there, they both have electron clouds. We'll do that one in blue for the front carbon. And we'll do it in pink for the other one. You can definitely see that there's going to be conflict. There's going to be some repulsion. All right. Now, in the literature, they also discuss favorable interactions. That when you are in the staggered conformation, you can have favorable interaction with antibonding orbitals. But I'm not going to go into that too much, as long as you understand the two principles that I just shared with you. And so what we have here is when they are eclipsed, there's repulsion, makes it higher in energy. And when that's in the staggered, there's less repulsion, lower in energy. All right? Now we're going to take a look at the conformations of butane. And what we need to understand about butane is we are going to take a look and we're going to take our eye and we're going to take a look down carbon 2 and the carbon 3 bond and look at the different conformations and look at the energies of those different conformations. And they're going to be, this energy diagram is going to look a whole lot different than ethane. So when we take and draw the Newman projection here as drawn, what can we see? And carbon 2 is going to be our front carbon. We're going to have a methyl group there. So this methyl group right there is that one. And then, let me draw my hydrogens. Then I have my two hydrogens right there. And then in the back, carbon 3 is the circle. So that means the methyl's right there. And then the two hydrogens right there. So what I want you to do, as I'm going to draw out the energy diagram and show you all the Newman projections, what you're going to look and keep track of is the methyl groups. Where are they with respect to one another? Right now, you can see that the dihedral angle between those two methyl groups is 180 degrees. And so you can see that this conformation is going to be my starting point. And then, as what I'm going to do is I'm going to take the front carbon and rotate it 60 degrees at a time and take you through this step by step. So what we can say at this point is when you look at every single dihedral angle in this Newman projection, what is the dihedral angles? They're 60 degrees. So we could call this guy a staggered conformation. Okay? We could call it staggered. But I'm going to introduce a new name to describe this because now we are focusing on the two largest groups that are on the front carbon, or the largest group on the front carbon and the largest group on the back carbon, and tracking their relationship. So when the two largest groups, which in this case is what? A methyl and a methyl, when they are 180 degrees, have a dihedral angle of 180 degrees, we call this conformation anti. So we have an anti-conformation here because those two largest groups are 180 degrees from one another. All right? So I'm going to erase this draw out the energy diagram, and then we're going to look at every single conformation. So here's the energy diagram, and you can see that this is different now because what we have is we have a low here, so 1, 2, 3, 4. We have 4 different energy levels that we are going to look at now. And I already talked about this lowest energy one, and that is when the methyl groups are 180 degree, have a dihedral angle of 180 degrees. And we call that anti. And that marker is not going to work. Let's try this one. That is an anti-conformation. And we can also say that it's staggered. And why can we say that it's staggered? It's because when you look at all the dihedral angles, they're all 60 degrees to one another. Now, please note that I'm just taking a shortcut here. All these right here are hydrogens. So I'm just not going to write that all throughout this demonstration here. Okay, so we have a name for the lowest energy, the 2 largest groups. When they're 180 degrees, they're anti. And when all the dihedral angles are 60 degrees from one another, that is staggered. Now here we have an eclipsed conformation. Okay? So that is, we would just call that an eclipsed because everything's, all the dihedral angles are 0. Okay. But then we come to this guy right here. We can look at it and see all the dihedral angles are 60 degrees. So we could say, hey, this guy's technically staggered. Okay. So we'll write it down here. Technically staggered. But remember, we are focusing our attention on these groups right there, the 2 largest groups. When the 2 largest groups have a dihedral angle of 60 degrees, okay, that has a really unique name, and it's called the gauche. Gauche. That's the gauche conformation. Right, and you can see that the gauche conformation right here is a little bit lower in energy than the eclipsed. All right. But then when we rotate another 60 degrees, we can see the dihedral angle between the 2 methyl groups right here are 0 degrees. All the dihedral angles are 0 degrees. So we can call this eclipsed, technically, right? All the bonds are eclipsing each other. But this guy, right here, you see it has the highest energy. And why would you expect this to have the highest energy? Because the 2 largest groups are next to each other. Okay? So just think about it this way. If you had 2 hydrogens that are eclipsed to one another, the 2 hydrogens are very, very tiny. So they're going to eclipse. They're going to be high in energy. But if you replace those 2 hydrogens with methyl groups, like this, and watch, I'll expand it out. Methyl groups are really, really bulky. And so if I just represent them by circles, you can see that they're much larger than a hydrogen. They take up more space. And because they take up more space, they're going to clash with one another. All their electron clouds are really, really close to one another, going to cause some problems. So this is going to be the most, or the highest in energy conformation, because it's eclipsed, which is high in energy, and when the two largest groups have a dihedral angle of 0, that is just bad, bad, bad. Okay? As we continue to rotate the front carbon, you can see now from this second half on, we're just going to repeat. We're going to then get the two groups the dihedral angle of 60 degrees. So that means this guy right here is in the Gauss conformation. This is eclipsed. And then we go back down to the lowest energy form, where it's the anti-staggered conformation. Okay, so now I want to talk a little bit more about this guy and basically go over some vocabulary and some explanation as to what's going on here, why this is so much higher in energy, okay? Okay, when we look at these two conformations and looking at their corresponding Newman projections, I've highlighted the anti-conformation, which is the lowest energy, and the highest in energy due to being eclipsed and the two largest groups having a dihedral angle of 0. Now, to explain these energy differences, we have two words. We have torsional strain and steric strain. Now, torsional strain, like I explained before, has to do with the electrons within the bonds. So what do we have here when we look at just some random, well, I already explained torsional strain, okay? So I don't need to talk about that again. I already talked about torsional strain. But what butane now introduces is what steric strain. And steric strain is a little bit different because it has to do with just atoms getting in the way. So if we take a look at butane in this conformation, we have these two methyl groups that we had to look at. Okay, and methyl groups are pretty large because they have these 3 hydrogen atoms that just take up space. Okay? And I could represent that methyl group just like with this big circle here. It just takes up a lot of space, right? Now you can see they're far away as possible. Okay? And that's a good thing because we cannot have atoms so crammed together and in the same place. If there's not space for all the atoms to fit, it just doesn't go in there very well. But then when you take a look at when it's in this conformation, hydrogen, 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 okay? They're a whole lot more bulky, or sorry, they're now very close to one another. And I didn't draw this very well. I'm going to draw it in a way that I can exaggerate this. Okay. Okay. So what are we seeing here? That these groups of atoms are in the same space. And when they're really, really crowded in the same space, we call that steric strain. So the reason why this eclipse conformation is the highest in energy is because it has the maximum amount of torsional strain because every bond is eclipsed. And then it has the maximum amount of steric strain because you have the two largest groups as close as possible to one another. And that is just going to say, nope, that's going to increase the energy. All right, so you got to remember those words and the differences in which they mean. Steric is just atoms getting in the way. Torsional is the electron clouds in the bonds getting really close to one another. All right, and you can see the torsional strain a whole lot better in this Newman because you have an electron cloud there, electron cloud there, just getting really, really close to one another. Okay. Let's see here. The next topic that is very important is something called chair conformations. And this is particularly looking at cyclohexane. The 6-membered cyclohexanes. What we're going to do is take the way we've been drawing this, like when we have cyclohexane here, we would draw wedges, and we could draw our dashes like this, right? But what we're going to now do is draw these molecules in a chair conformation. And in order to do that, let's start with the most simple one right here, okay? And it looks like this. And I'm going to draw it really quickly, and then I'm going to show you step by step of how I do it. Okay? So we'll just clean that up a little bit there. So what we have here is 6 carbons. You can number them 1, 2, 3, 4, 5, 6. And you can see that it has 6 carbons. Okay? So this representation and this representation say the same thing. One difference, though, is in this structure here, if we draw a wedge and a dash, okay, like that, like this, what is going to happen is on the chair, we only have lines, no wedges or dashes. So like on carbon 3 here, we would have a bond coming straight up, and then another bond that looks like that. All right. And then if we had a bond on carbon 2, we would have one that would come straight down like so. Do you see how I put a gap between the two right there? And then you would have something that looks like that. So there's no wedges and dashes on the chair conformations. But what we're going to learn shortly, depending on if it's pointing up or pointing down, will correlate back to if it's a wedge or a dash on this molecule. Okay? So let me show you stepwise how I draw my chairs. Okay? Don't worry about these groups or these substituents. Don't worry about that. Let's just worry about drawing the chair. Okay? Step by step. How is that done? So we will draw a reference here. This is what we're drawing is the chair. What you want to do is you're going to take 2 parallel lines at a slant. You draw one line, and then you're going to draw another line parallel a little bit down, but I go basically right in the center, and I go down, and then I go and make a parallel line of the same length. So if that's 4 inches, that's 4 inches. All right? And then I just make a triangle to connect them both. Down, boom, and then you can see this one right here goes up, down, like that. And so what you want to see happen is you're going to have 3 parallel lines. That's parallel. That's parallel right there. And then you can see there. Okay, they have the same angle here. If your chair doesn't have 3 parallel lines, then it's not drawn right. Okay. So what if could I have drawn a chair like this? So this blue one, how did I start? So this blue one, I started like this, like that. What if I drew it at a different angle? What if I drew it this way? Like that. So, see, I didn't make that connection there very well, did I? Like so. Both are correct. All right. Yeah, you can see that they look a little different, but they're both correct. And both are going to be needed. What's going to happen is you're going to have to be able to draw it like this and like this. And we will talk about that as we progress through this lecture here. But that's how you do a chair. So this chair that I drew here looks a whole lot better than these two right here. These two I went a little fast. Okay? So it takes practice, lots and lots of practice. But it's very, very important that you get these structures drawn correctly, because when you are given an exam, you're going to have to draw these structures. And if they're not drawn appropriately, then it makes it very difficult for the graders to know what you're doing. Okay? So there's a lot more that we are going to say about these chair conformations that we are going to start looking into right now. Okay? Now, if we have a chair, like I said, there's not going to be any wedges or dashes. We could have a bond straight up. Okay, so you look at every apex, every point, and it's either there's a bond that's going to be straight up or straight down. And so you can see these on the ends are really easy to draw. Okay. These two carbons that are on the inside of the chair, you see how it's pointing up, so I go up. This one's pointing down, so I draw it down, just like that. Okay. So those bonds, when they're up like that, directly up or directly down, in that fashion there, okay? Well, let's see here. So those bonds right there in green are going to be called axial. So those are axial bonds. Okay? Now I'm going to draw another chair just so it doesn't start getting really messy. And then we're going to combine everything, okay? So if I draw myself another chair here, let's do it here. Like so. And then when you look at the same carbons here, and if you can draw what's called an equatorial bond. And an equatorial bond is when you look at this carbon here and you want to draw the equatorial bond, you skip this bond, and then you go to the next one. And so this next bond right here is the same angle you want to draw the equatorial bond. You see that there? And then how would this equatorial bond look on this carbon? Skip the bond, go to the next one. So it wants to be like that. That angle. Now if I do these two ends, skip it, this one. Okay, so that one has to be like that. Right there. Let's see here. Like that. And then this one, skip boom, would have to look like that. And those are called equatorial bonds. Now let's draw a chair conformation with all, well, wait, I forgot to do the interior equatorial. Okay. And so this one would be, that's an equatorial bond. And then this one right here, let's see here. Up, down, equatorial would be we skip and then like that. So we skip the first bond and then we look at this one and say, okay, that has to be at that angle, like that. All right. So I'm trying to get this bond angle to match this bond angle right there. And the equatorial bonds right here go outside of the ring. They're not going to be like these axial ones where they go through the ring. Okay. So those are the two different types of bonds that are going to be on a cyclohexane ring. Now when we combine them, okay, you're going to see that it gets a little bit messy. But if we start out simple, let's just start out simple for a second. All right, clean that up, make sure the bonds are good. What we can have happen here, to keep it simple here, that guy is axial. And then this guy is going to be equatorial. All right. And so you can see that this is going to get a little messy when we put it all together. So those in orange are our equatorial bonds. And now in green, I will put in the axial bonds. All right. So you can see that it's going to get really, really complicated. Or not complicated, just messy. Because if this is my molecule here, our cyclohexane, what are on all these axial and equatorial bonds? They're just hydrogens, right? So you would just put in hydrogens for every single one here. Like that. So that's the chair conformation of cyclohexane. But when it's cyclohexane, you typically don't draw in all the axial and equatorial bonds because it just gets really, really messy, right? And so we're organic chemists, and we like to make things easy or make it more simple. So that's what you're going to do. But when we start adding substituents to the cyclohexane ring, then we start drawing in our hydrogens and the things that are important. So for example, if I drew in a methyl group right here, CH3, and I'm calling that carbon 1 and that's carbon 1, then we would draw in our methyl group. And then we could draw in as well the dashed hydrogen. Now, when we take a look at this cyclohexane ring right here, it is monosubstituted. We have added one substituent, the methyl group. Okay? And so when we look at this chair right here, when I point to the methyl group, Is it axial or equatorial? Hopefully everyone say, hey, that's axial, that's equatorial. All right? But there's this idea called a ring flip. And a ring flip is an equilibrium process here. Okay? And what's going to happen is this carbon right here is going to flip up. Okay? And this carbon right here is going to flip down. So this ring flip that I'm referring to is not taking, let's say, it's not taking the cyclohexane ring, and if I represent the cyclohexane ring as like a pie, so it's just a circular pie, what I'm not doing is taking that pie and flipping it upside down. That is not a ring flip of what I'm talking about here. A ring flip, when it comes to cyclohexane, is when you look at these puckers. You see how these two bonds come like this, and there's this pucker? A ring flip is making that pucker go like this. Okay? So if we number these carbons so we can track what's going on here, if I call that carbon 1, 2, 3, 4, 5, and 6, what we're going to do is a ring flip, which is basically changing the pucker. And so what you have to do a ring flip is you're going to take the way that you drew this ring, or this chair, sorry, and the way I started this chair was I drew these two bonds right here very first. Okay? You have to do the exact opposite for the ring flip. So that means I have to come in at this angle like this. Okay? Not perfectly parallel. And then like so. So what I've done is a ring flip. So the way I drew this one, I have to do the opposite on this one. And look at what happens. This carbon 1 right here puckers up. So that number 1 carbon is now right there. If that puckered up, then that carbon 6 had to pucker down. And so that would be carbon 6. So 1, 2, 3, 4, 5. All right, see that? So carbon 1 puckers up, carbon 4 puckers down, and that's what we see. 1 is there, 4 is there. Once you figure out where carbon 1 goes, you just number in the same order that you did. You went 1, 2, 3, and numbered it. Now, something to note, that this numbering scheme is not used to name the molecule. Okay? I'm just using these numbers to keep track of where the carbons are so you can see them. I'm not using it for IUPAC purposes. So now what has happened is the methyl group here in this ring structure, okay, is axial. But when you do a ring flip, everything that's axial goes equatorial. So I see that this methyl group is attached to carbon 4. It's still going to be attached to carbon 4, but the question is, and I'm running out of space, is it going to be axial or equatorial? So let me redraw this ring a little higher up so we can see it. Okay. So there, I just redrew it. And so if this methyl is axial on this ring, when we do a ring flip, it's going to have to be equatorial on the other ring. So that means this methyl right here is this methyl here. You can't really see it because it's cutting off the board, but that's our methyl. And then this hydrogen is equatorial, so that means it has to flip to the axial. And so there is the hydrogen. To see that, maybe I should write it. This one's equatorial. When we do a ring flip, it now turns into the axial. And that is very, very important to be able to see. So in summary, for this little part here, everything that's axial on this ring is going to be equatorial on this ring when you flip it. That is very important to know. Now, why should you care about this? Because look at what's going on here. It's different conformations here. One is more stable than the other. And so we need to understand the energetics here and which one is going to be better for, or which one's going to be lower in energy. Okay? So let's take a look at the energetics here. So let's draw ourselves a monosubstituted cyclohexane ring, and I'm going to put a methyl group there. Now we want to do a ring flip. This would probably be a good spot for you to pause the video and draw the ring flip and see what you come up with. Okay. So let's draw this one. Let's actually change this guy to, let's put it right here. Okay. Just so we can look at a different version here. Now when we do a ring flip, I started with these two bonds right here. So now I have to, they're slanting this way. So now I have to draw them in the opposite slant, like that. And that's like so. Sometimes the chairs just don't come out the way that you envision. So you can number this however you want, as long as you are consistent. So if that's carbon 1, what's going to happen when we do a ring flip? That's going to go up, that's going to come down. So we have carbon 6 here, 1, 2, 3, 4, and 5. Okay? So what is the answer here? What does our product look like? Well, carbon 1 is there, carbon 1 is there. This methyl is axial, so we have to draw it equatorial over here. And when we draw equatorial, what do we have here? We have a hydrogen now coming down there, because what do we have here? We have a hydrogen there, which is equatorial, so now it's axial. So our methyl group has to match, skip a bond, this bond. It needs to be parallel with that guy. And it's not the best, but almost, okay? But we have to understand that this is equatorial, so I'm drawing it slanted. Okay? So that's in the equatorial position here. You know something? This may not suit my purposes. The answer is still the same, but you may not see it as well. So I'm going to redo it really quickly here. I'm going to put the methyl group back over here. And when we do the ring flip, we would have this, like that. And so our methyl group would be right there, equatorial. Okay? So I'm just doing this because it's going to be easier to see. Not that the answer is going to be different. The answer is the same for doing it up here or down here. Okay? So this one is axial, this one's equatorial. At equilibrium, which one is favored? Kind of like, it's, let's see the numbers here. This one is favored by 95%. This is 5%. Why? Because when you have large groups are more stable in the equatorial position. So hear me out, write this down. Whenever you have a cyclohexane ring and you have large groups, you want them in the equatorial position. They're more stable. So it begs the question, why is this one unstable, or the least stable between the two? And it has to do with this concept called 1,3 diaxial, let's see here, axial interactions. And that has to do to the fact that when you look at these carbons right here that are pointing up, like so, and then this one, we have a hydrogen right there. What happens is if you look at those hydrogens and those groups of atoms as a ball of electrons, and then this methyl is pretty bulky, right? So we can represent that guy like this. You see how big that guy is? Because it's so big it's big, and when it's in the axial position, it's going to interact with the other axial groups. And that's going to increase its energy, and it's not a stabilizing effect. It's a destabilizing effect. When you have the bulky group or the large group in the equatorial position, you do not have the 1,3 diaxial interactions, and so it is more stable, lower in energy. Okay? So looking at the time here, what we will then do in class is we will practice these chairs, and you're going to be introduced to looking at di-substituted and tri-substituted cyclohexane rings. And you're going to have to be able to take a ring that looks like something that looks like this. Okay? And we could put a chlorine there and a bromine there, or whatever group we want. And then you have to draw the appropriate chair. And then you're going to have to say, after you draw the two chairs, which one is the most stable one? And you're going to use this principle right here, the 1,3 diaxial interactions, to figure that out. Okay, so with that, that's where we will end this video for today. And if you have any questions, just let me know.